start with this one, and I just want to show you all what is it that makes this a good GMAT question. What makes a good GMAT question is when you could solve it mathematically using textbook math, but it's not particularly convenient. And alternatively, you could just use some good reasoning to solve it, and that's going to be a much more efficient, much quicker way to solve. When you see a question that doesn't really have a benefit for people who use their reasoning, then that's not a good GMAT question, and that's what the Veritas Prep question that you shared is like. So we'll get to that one. But first I want to show you, how do you use reasoning to solve this particular question? Because mathematically, yes, you can solve it, but it's not very convenient or quick. And what you would want to do is start by saying, look, I've got a ratio of 1.5 to 1, which really I should expand by a factor of 2 like that. And this is a ratio that describes how quick each pump is on its own. You've got your fast pump and you've got your slow pump. And we can see here that the fast pump is 3/2 as fast as the slow pump is. How did I get 3/2? Just from that ratio, 3 to 2, 3/2. Then what you would want to do, and this should really be automatic when you have a ratio of a fast pump to a slow pump, is to talk about how fast they would be together. And how fast would they be together? In this case, it would be 3 plus 2 equals 5. So because rates are additive, you can add them if they're working together. You can add the 3 and the 2. And the reason I point that out is because times are not additive. Times, if Jackie takes 2 hours to do something and I take 5 hours to do the same thing, then together Jackie and I won't take 7 hours. That's nonsensical, right? If he can do it in 2 hours on his own and then I'm helping him, why would it take 7 hours? So times are not additive, and that's a very common mistake people make. But rates are additive. So if his rate is 5 units per hour and my rate is 7 units per hour, together we have a rate of 12 units per hour. You would add those rates together. And that's why I can say that together this would be, how quick are they? They're 5 ratio units of quickness, if you will. Okay? Then we can say, look, I have some information about how long it takes them to do the job together. I want to know how long it would take just a fast pump on its own, so I need to have some way to compare how quick are they together versus how quick is the fast pump on its own. So if these are the rates, and I'm interested in the times, and I'm really only interested in the time for the fast pump on its own and the time it would take them together, because I have information about the together and I want to know fast pump on its own, you just do this kind of crisscross because of that reciprocal relationship between time and rate, meaning the faster you are, the less time something would take you, and the slower your rate, the longer it would take you. So there's this kind of reciprocal relationship between them. And you would say, okay, so in terms of time, the fast pump on its own would take 5/3 as long as they do together. But we know how long they take together. That was given. 4 hours. So the fast pump will take 5/3 of 4 hours. Now, after a bit of practice with these kind of ratios and flipping the ratio because of the reciprocal relationship and all that kind of stuff, this solution can be done almost in your head. I would still write down the ratio because why not, but we're talking 20 seconds to solve this problem. But you have to practice using ratios for these types of rate work questions. So I want to pause here and answer any questions, because I know that if you've never seen this kind of solution before, it can take some wrapping your head around it. I'm looking at the fast pump and the 2 pumps together. The slow pump ends up not being that interesting in this question, because look at what we have and look at what we want to have. We have the time it takes them together. We want to know the time the fast one takes on its own. So the slow pump is really just there as a way for us to infer how quick they are together. And once we've made that inference, so we started with a 2-way ratio, fast to slow is 3 to 2. We made an inference, we turned that 2-way ratio into a 3-way ratio by putting in a third column there to represent how quick they are together. And once we had that inference column, from that point we could just ignore the slow pump on its own because we don't know how long the slow pump takes on its own, nor do we want to know how long the slow pump takes on its own. So the slow pump is the least interesting thing in this problem. We only needed it temporarily to create that inference column. So you can't actually apply this kind of reciprocal relationship to more than 2 columns at a time. It just gets too messy. So I wouldn't recommend that. I would say get all the columns that you're interested in, and then decide which 2 of all of those columns, which 2 do I want to flip, to go from ratio of rates to ratio of times, or vice versa. But I wouldn't try to do that flip-flopping with more than 2 columns because it gets very messy. It's not simple. I've never done it myself because there's never really a need to. There's never a need to. Just set up the columns you're interested in and then decide which 2 do I really need, and then flip those 2. And I do think it's also important to write down the word rates and write down the word times so that you don't get confused. You want to know, what does this ratio represent? Is this a ratio of their times, or is it a ratio of their rates? And there's also a way to kind of sanity check what you're doing, because look at how I named them, fast pump and slow pump. Surely the fast pump should have the bigger number if we're talking about their rates, and the smaller number if we're talking about their times. So that's a way to just kind of make sure that what you did makes sense. Yeah, that's right. So, and there's an important takeaway there, which is always keep your eye on the prize. What do I know? What do I want to know? What do I know? What do I want to know? That's how you learn to be more efficient on these questions. And it's not just that it's much faster, it also drives a much deeper understanding of the situation. And when that will become important is in difficult data sufficiency questions. That's the best example I can think of, because in data sufficiency we don't actually need to solve it. Your algebraic solution, that works for getting to the right answer, but it doesn't drive that deeper understanding where later on you can look at a hard data sufficiency question and just intuitively know what's sufficient and what's not sufficient. But when you use this kind of approach, right, so you're thinking about, I know the ratio of the fast one to the slow one, what would I be able to infer if I wanted to infer it? Well, I'd be able to infer how fast they are together. Then if I wanted to, I could figure out any ratio I want from there for how long it takes them to do stuff. So it just drives a much deeper level of understanding of the concept than you would get from just solving it algebraically. I would also say that with the algebra, you're not really learning anything. Like once you know how to solve it algebraically, and then you do this practice question at home, let's say, and you solve it algebraically, well, you didn't learn anything from it. You clearly already knew how to solve it algebraically, and now you still know how to solve it algebraically, but it was kind of a waste of time in that sense, because you didn't improve your reasoning as a result, you didn't grow as a GMAT test taker as a result, you were the same person you were before you did the question. So that's why I'm such a big fan of always looking for reasoning-based solutions, because that actually makes us smarter in a sense and will push our GMAT score up. All right, so now let's look at this Veritas prep question, which doesn't really have a great reasoning-based approach, which makes it not a very good GMAT question. I've never seen an actual GMAT question that looks anything like this. This is very complex. I'll give you all 2 minutes just to look at it. As I said, it's not a very good GMAT question, so we will have to do some math here. The math would have to look like the following. We'd first have to say times are not additive, so we need the rates. And the rates would be 1 over x, 1 over y, and 1 over z, respectively. Let's say that, we'll take the example that we had earlier, where Jackie takes 2 hours, and Avi takes 5 hours to do some job, okay? If Jackie and I collaborate and we do this job together from start to finish, who is going to do a bigger fraction of that job, Avi or Jackie? You, Jackie, would do a bigger portion of the job, that's right. And why is that? Exactly, you're faster. You're faster at it. We're starting together and finishing together. You're faster, therefore you'll do a bigger fraction of the job. But let's take this one step further. What fraction exactly of the total job would Jackie do, and what fraction would Avi do? That's right. You could say j to a, when we're looking at times, it's 2 to 5. Now be careful, everyone. You don't want to have it together for the times. Right? Don't make this mistake. That's wrong. Because times are not additive. But then, when we talk about rates, you can do this. So Jackie is 5 halves as fast as Avi is. And now we can say this. Now we can add them, because now we're talking about rates. And this is what JD was saying. He was saying the ratio of how quick they are is 5 to 2 to 7. Now, Jackie, can you look at this three-way ratio that we have here in purple and tell me what fraction of the job would each of us do? That's exactly right. So the ratio of work done will match the ratio of the rates. Does that make logical sense for you? Like whoever is faster will do more of the work, and they're positively correlated. So in this example, Jackie would do 5/7 of the total job, and Avi would do 2/7 of the total job. So taking that understanding back to the Veritas Prep question, we have the rates. Really, we should call this minus 1 over z because it's a drain. It's doing the opposite work. So we have the rates. And we wanted to know what fraction of the total amount of work alpha would have done. Out of the total amount of work, what fraction will alpha have done? So using the same thing we just discovered in the other example with Avi and Jackie, we could say, look, these are the rates. They're 1 over x to 1 over y to negative 1 over z for a total of, together, what would be the rate? It would be 1 over x plus 1 over y minus 1 over z. That's the combined rate. So how would you derive from all of this what fraction of the work alpha did? This out of this. Just like we did with Avi and Jackie. Does that make sense? And then it's just a matter of some algebraic simplification and you'll end up with a correct answer. But it's really not a good GMAT question because just solving this, it's highly unlikely that we would have to do such a thing on the GMAT. And even if we did have to do such a thing on the GMAT, that would be the entire question. Like they would ask us to simplify this. That would be considered an easy question. But I've never seen a question where you had to do all of this kind of advanced thinking, and then after all of that, you still had to translate something that ugly to what answer choice B looks like. So it's really not a very good GMAT question. And I would say, yes, we want to be able to solve such a question, but you don't have to do it in 2 minutes, because it's not a real GMAT question. So if it takes 5 minutes, I think that's perfectly fine. And I'll just repeat my general advice here, which is stick to official GMAT questions because it's very hard for test prep companies to write good GMAT questions. And this is not anything against Veritas Prep. I think the same thing for all test prep companies. It's part of why I don't create my own questions for quant reasoning, other than some very simple examples in the book. But outside of that, I really avoid creating my own questions because it's just impossible to write really good representations of true GMAT questions. This is from the official guide. You can see the source there at the bottom right. And it'll give us 2 minutes again. So that's time. Any volunteers want to talk through how they thought about this? I'm not sure that I follow the point about a ratio in statement 2 because statement 2 is describing a difference between two numbers. And knowing the difference between two numbers does not allow us to infer the ratio of those numbers. For example, if I say that I found $100 on the street, that means that my net worth has gone up by $100. So that's a difference of $100. But it would be impossible for anybody to know whether that was a big deal or not a big deal for me because you don't know how rich I am to begin with. Or maybe I'm homeless and $100 extra meant that I went from a net worth of 0 to a net worth of 100. Or maybe I'm Bill Gates and the $100, I don't even feel that. So that's what I mean when I say knowing the difference doesn't allow us to infer the ratio. Or it's like if I said there's a married couple where the husband is 12 years older than the wife, right? Now, is that really inappropriate that he's 12 years older than her? I don't know what the ratio is, right? Maybe he's 72 and she's 60. That seems reasonable. Maybe he's 20 and she's 8. So knowing the ratio often gives us a lot more context than just knowing the difference, and you can't infer one from the other. So that's my reaction to your point about statement 2. My reaction to your approach in general is that you seem to be relying maybe too heavily on translating the words into an equation at the expense of thinking logically about the story. Now let me kind of illustrate what I mean by that. Looking at the free info and looking at statement 1, the big question mark in my mind is, how many children are there? Are there just a few children, or are there a million children? I can't tell based on statement 1 on its own. And I think that because you were so busy building an equation for statement 1, you missed the fact that we have absolutely no idea whether there are just a handful of kids or a million kids. Both of those are possible. We just don't have any information about the situation with the children. Do you see that now that I mention it? Well, actually, the number of adults can be calculated with statement 1, because we know how much a ticket cost and we know how much they spent for the adults. So we could infer how many adults there are precisely using statement 1. But we'd have no way of knowing how many children there are. And I think that that's easier to notice if we don't have our heads down busy building some equation. And the 10% discount here really is just a distraction, because it's data sufficiency. So whether it's a 10% discount or there is no discount or it's a 40%, it doesn't matter. Because we don't need to actually solve anything, we just need to think about what do we know and what do we want to know. So in this case, we know how much each ticket cost for an adult, and we know how much each ticket cost for a child. And then statement 1 tells us that, or implies exactly how many adults there were, right? You could figure it out if you wanted to, but we have no idea about the children. So without putting pen to paper, I'm doing a better job than you did with a lot of pen and paper. And I think that's instructive. I think there's an important takeaway here, which is, don't rush to use pen and paper. First, just take a bird's eye view of the story and think about it logically. What do I know and what do I want to know? I know the price per ticket for adults. I know the price per ticket for children. Do you see what I mean when I say that the 10% discount is a distraction?
So you're saying you don't even write times 0.9 on your paper?
Not at all. Not at all. Not in data sufficiency. God, no. No. My takeaway from the free info is that we know the price per ticket. Exactly. Exactly. I don't think you would have misread it if you weren't using pen and paper, right? If you were just kind of trying to relax, leaning back in your chair, taking it all in, reading very slowly. I read very, very slowly on the GMAT. And I have all the time in the world to read very slowly because I'm not working hard. I'm not writing stuff. Now, there are some cases where writing something down actually helps you to digest it. But copying stuff down never does, in my opinion. And when you are writing something down, you really need to think about, is this adding any value for me? So an example is those two pumps, the fast pump and the slow pump. We were told that the fast pump is 1.5 times as fast as the slow pump. We did that earlier today. There, I think it's very useful to write down in your paper, fast to slow is 3 to 2. And then put in a third column for your inference, that together their speed is 5. That's value add. And that actually helps me to digest the story in a deeper way. In this case, writing down 0.9 multiplied by some number, just so that you have on paper the price per ticket, who cares what the price is? I just want to know that we know what the price is. I know the price per ticket for adults. I know the price per ticket for kids. That's it. That's really all I need to take away out of all that free info. And the fact that there are, more than 10, or at least 10 people in the group. That's it. So we know there are at least 10 total. We know the price per ticket for adults. We know the price per ticket for kids. And then you go to statement 1. And you say, okay, I could figure out what the number of adults is. Of course, you shouldn't actually figure out what the number is. Just note that you could if you wanted to. And then ask, okay, but how many kids are there? Because the question is not about how many adults are there. The question is about how many children are there. And my answer to that is, I don't know, could be 5, could be 1 million. And then you can eliminate AD. Now, statement 2 is actually much harder to evaluate. Any thoughts from anybody about statement 2 before we jump in? So Babar is partially right. Babar is saying that statement 2 gives us the difference between the total amount spent on kids and the total amount spent on adults. So that's correct. It is giving us that. Where I think you might be a little bit too quick to jump to conclusions is to think that if we know the difference between two amounts, we would be able to infer what those amounts are. I mean, going back to my example of finding $100 out in the street, okay, so my net worth grew by $100, but what was my starting net worth and what was my ending net worth? I don't know. Knowing the difference between two values does not allow you to infer what those values are. Now, there is a complication here, which is the integer constraint, right? We know that it's not just a difference between two random numbers. It's a difference between some multiple of a number, right? That number would be 0.9 times 5,500. So a multiple of that versus a multiple of whatever the other number is, right? 10% below 4,800. So we're talking about a difference between two specific multiples. But what I'm imagining is, can I take that distance on the number line? So I'm imagining, right, two tick marks on the number line, the distance between them is 4,860. Is there a way to push those tick marks up the number line by the same amount? Because I want to keep the gap between them 4,860. Because that's given. We know the gap between them is 4,860, so I need to keep that the same. Can I move the tick marks as they are up the number line and at some point reach a place where, again, one is a multiple of what it needs to be and the other is a multiple of what it needs to be? So that's the kind of thought experiment that I have to go through here, because I'm wondering, is there only one unique position on the number line where you'd find such a gap between such multiples, or would that happen every so often on the number line? And if you've never thought about that before, then that takes some thinking. So let's think about this together. I'll go back to showing my face. How would I think about that? I would take a much simpler case. I would imagine that we're looking at a multiple of 5 and a multiple of 3. And let's imagine that the difference between them, so I'll take, let's take like 7 times 5 and 5 times 3. So 7 times 5 is 35 and 5 times 3 is 15. The difference is 20. Could there be, up the number line, another position where you'd have a multiple of 5 and a multiple of 3 that are exactly 20 apart? So think about that for a minute. When would it happen again that the difference between a multiple of 5 and a multiple of 3 is 20. We'd have to add the same quantity to both of them, but we still want to end up with a multiple of 5 and a multiple of 3 respectively. So what quantity could you add to a multiple of 5 and a multiple of 3 such that they will still be a multiple of 5 and a multiple of 3?
LCM?
Bingo. Right. You want to add the LCM of 5 and 3. So if I add 15 to both, this would now be 10 times 5, and this would now be 10 times 3, and the difference between them would still be 20, because we added the same amount to both. So we still have a multiple of 5 minus a multiple of 3, and it still gave us the same difference. So now I'm convinced that statement 2 was not sufficient on its own. As long as we add the LCM, the least common multiple of the integers that we're dealing with, in that case it was the cost per ticket. So as long as so whatever the cost per tickets are, you could find the least common multiple of those costs and just add it over and over and over again, and you'd still have a multiple of one versus a multiple of the other with that same gap of 4860. Which means statement 2 is not sufficient on its own either, and we can eliminate B. From statement 1, I know how many adults there are, and I know how much they spent. Statement 2 tells me that the adults spent more than the children, I believe, right? No, other way around. The children spent more than the adults. But I know how much the adults spent. Statement 1 told me how much the adults spent, so if I know how much more than that the children spent, well, now I know how much the children spent. And if I know how much the children spent, and remember we know what the cost per ticket was, now I can infer the number of children. So I think that's a better way to think about it than thinking about X in the context of some equation that you wrote in your paper. Is it just me, or is any of you noticing that you might do better if they take away your yellow scratch pad? Like if you're not given an opportunity to use pen and paper, certainly on some questions that would be an advantage. I do think there's a negative correlation between the amount of ink you use and the score you get. So I would encourage you when you're practicing these questions at home to not, and I think I might have said this last week as well, your default shouldn't be having a pen in your hand. Only pick up that pen if you truly have some value add to write down, like in the example of the 2 pumps. In this question, I don't think that I would use pen and paper, and if I did use pen and paper, it would just be to draw a number line and put 29.7 and then add 4860 to the right of that, just to kind of get a visual representation of what we know and what we want to know. Yeah, you can't go to the test center and do it there for the first time. You have to build that confidence over time doing these questions at home. But probably the most important thing that I can teach folks for the GMAT is do not focus on getting the right answer at home. Getting the right answer is totally useless. You don't learn, you don't improve your confidence or your reasoning or anything from picking the right answer. You improve all of those things from analyzing the question very deeply, the way we did here. I mean, this little segue that I did over here, right? Now I really know on a very deep level that a particular gap between 2 multiples of numbers will repeat itself every time I add the LCM to those multiples. These were representing the ticket prices. So I was imagining that an adult ticket is $5 and a child ticket is $3. And then I just pulled out of nowhere, really, the 7 and the 5 just to have an example, right? So imagining that there are 7 adults and 5 children, would there be another position in the number line? And there was, right? 10 adults and 10 children ended up giving us the same exact gap. So I just constructed a simpler situation just to kind of explore it further. You can't do that in the middle of the test. But if you did it at home, then now you don't need to do it in the middle of the test. And this is what I mean when I say don't focus on picking the right answer. Focus on learning from the question. Now, this is a really good reasoning-based analysis of statement 2 that will enable me to solve such questions much easier in the future. Oh, I see what you're saying. It's because these multiples that we're talking about, when we say, oh, there's a difference of 4860 between two multiples, going back to the original question. Right? There was a 4860 difference between a multiple of one thing and a multiple of another thing. The constant, the thing that was given to us, that we can't play around with, is the ticket price. So we're talking about a multiple of the ticket price. Which multiple of the ticket price depends on how many tickets. But the how many tickets, that's something that's not constant. That's something we can play around with. That's what we're trying to find out, is how many tickets. But what we know for a fact is the price per ticket. So that's why I'm talking about a multiple of the price per ticket for adults and a multiple of the price per ticket for the child. Because the price per ticket is the thing that was given. The total spent by adults has to be a multiple of the price per ticket of an adult. And the total spent by children has to be a multiple of the price per ticket of a child. So the LCM would be the LCM of the prices per tickets. And you know, maybe what I should have done to make it a bit easier to follow is to define somewhere here, right, that this is the price per adult and this is the price per child. And then we're talking about how many adults and how many children. So could have 7 adults and 5 children, or could have 10 adults and 10 children. And what we're adding there, this plus 15, that came from the LCM of price per child and price per adult.